Okay, we're rolling. So happy to have you here. Welcome to the 9th lecture of privacy preserving natural language processing. And finally, we know everything we need to know in order to get something fun and useful in everything we learn about privacy and in particular in differential privacy to use it for NLP, which is the title of the course. And I want to highlight that, I mean, we're going to be talking about NLP, but mostly about research. So I mean, this is still part of, as you will see later, this is nothing you can use out of box and sell it to companies and say, like, your data are private with me, unless you have very good lawyers or, I don't know, I mean, you can convince them. I mean, people are selling things, but you will see the difficulties of doing privacy for real in NLP. So this will be about research, and I will highlight a couple of research that my group have been doing or what others have been doing. So this is not like, don't take it as a self-promotion, but take it as something where we have like first an experience on in terms of research. So I know a little bit what we are talking about, but there's tons of other research. Feel free to to look around. So this should be a mix of something what my group have been doing and what others have been doing in this area. So, well, actually, so we'll recap things and what we covered so far. This is just basically checklist that we kind of know where we are. So we talk about differential privacy, local and central. So today we'll be talking about the central, actually. The local one maybe we'll leave for next time. We know what approximate epsilon delta the differential privacy is doing, and we talk about a couple of mechanisms, from which one of the most interesting one is the Gaussian mechanism, because as we saw last lecture, it's actually very useful for this differential privacy stochastic gradient descent. So this was the last lecture, and we knew that for this DPSGD, we need the Gaussian mechanism, so epsilon delta, and there are a couple of other tricks, such as the composition and what was the other? Subsampling, so amplification by subsampling. So a couple of tricks, but DPSGD is a thing. It's a hammer in the toolbox. And today the question is like, well, what can we use this hammer for? I mean, is it good for everything? Because if you have a hammer, everything is a nail, right? But maybe like not all nails are actually good for this hammer, or maybe the hammer is actually not a good tool for everything you have out there. Okay, so we're good. Now we're talking about practical application of DPSGD, because this is the most used algorithm for privacy in for differential privacy in NLP, for protecting models that they don't leak training data, basically. So we'll be talking about this today. And just the recap of this DPSGD. So this is the last slide from the last lecture. And if you haven't had a chance to look into this paper from Martin Abadi and others, actually, this is actually quite accessible paper. So there is more words than mathematical equations, which is not the case for most of the DP papers, where this is just basically looks like Chinese characters if you look at it, full of math. This one is actually pretty well written. So there are some nitty-gritty details of the proofs, but if you read a paper, you will kind of understand pretty much everything what they're trying to do, like on a high level. So I actually recommend to look into this paper if you're interested in this DPSGD thing. Optional, so this is not required. I mean, I won't be asking any questions from this paper, obviously, but this is very accessible one, to be honest. So DPSGD is the de facto standard for supervised training with differential privacy, and there are some implementations such as a tool called Opecus, which you can plug into PyTorch, for example. The original implementation, was in TensorFlow privacy, and there might be others in some are written in Rust and things like that. And the tricky part is that the data points must be independent. So we have a table of entries, and this is the main assumption in DP, in differential privacy. And there's technical issues because in DPSGD, if you remember, in the algorithm, we were applying the noise to the gradient. So in each step we ask, what is the gradient given this point, or given the batch? Yeah, exactly. Given this one single example, not for the batch, for one single example, what is its gradient on the the gradient of the loss with respect to the parameters, basically the partial derivatives. And this is unbounded, so we're clipping by the L2 norm. So basically fitting everything to one sort of a circle or a ball. And this is costly. because you have to do it for every example, compute the gradient, the norm, and clip it. And if you want to parallelize it, you're kind of, good luck. I mean, so out-of-box parallelization is not easy, but there are tricks to do so. Okay, so this is DPSGD. Any questions or anything which is kind of like unclear on the high-level thing? So SGD is for training any neural networks, and with DPSGD, we kind of guarantee that any single instance or any single example in the training data set will be protected by differential privacy. This is it. Nothing less, but also nothing more. And this nothing more is going to be kind of tricky, as we see later. But anyway, so I'll split this lecture into kind of 4 case studies, so to say, by their, I would say, like trickiness. So we have 4-1, like the obvious application is supervised training. So the obvious application of DPSGD is just you train something. Then there will be less obvious applications. Then will be something where things go tricky. And then the last one I keep for like where things, I would like to say like where things go wrong. I don't think wrong is a good word, like very tricky. So it's really part of active research fundamentally. You will see later. But let's start with the obvious things, supervised training. Okay, so what can we do with that? So the question here is how differential privacy stochastic gradient descent works across various NLP tasks. And so this is actually a paper initiated by Timur, who was a PhD student in my group, and Manuel Senge, who was actually, at that time of this writing, he was a bachelor student, and he wanted to do some cool bachelor thesis. So as you see, like it's possible to do a thesis and to turn it into conference paper. So we get this paper published at EMNLP, so one of the top conferences for in the ACL family. So that's when I told you like I'm inviting all the people to join my group in any stage of research. What we're trying to do with bachelor or master thesis mostly is to turn it into papers. And we actually had it actually worked a couple of times to turn it into an ACL paper, ACL findings paper, EMNLP paper, LREC papers, and stuff like that. So that's what I'm trying to do with students, to like do actual research that matters. So in this particular research, we're asking, well, okay, we have this hammer, DPSGD, so we know you can take a data set and train on this data set, so no single example from the data set should be leaked. Awesome. Yeah, how will it work for what we know in NLP? In NLP, we have like dozens of tasks or thousands of, well, hundreds of different tasks, hundreds of different architectures. So we can start with simple networks up until to GPT and different training scenarios. So we're asking like, yeah, which training strategies and which models are actually the best for trade-off between privacy and performance? Of course, so as we might understand now, this is always a trade-off. The more privacy, the less accuracy or performance you get, and vice versa. So there's still a trade-off. You need to kind of decide for your own. And how exactly does it perform? So if we have, if we kind of decrease the epsilon, so the lower epsilon, the better privacy. If you decrease the epsilon, things will go wrong, but maybe they will just be completely rubbish. So this is the question. So we look into a couple of data sets and, well, basically a couple of tasks. So if you're not familiar with NLP and their tasks, so I'm going to just go through the table. I mean, and okay, so what I'm talking today about, like, it's not that you remember things from a table or data sets. This is not the case. That you should get a general understanding of where it could be useful, where not, and what are the trickiness. So I'm not going to ask you, what is the IMDb data set or how big is that? I don't care about it. I mean, you can look it up, but you should kind of understand the general applications of DPSG. So we look into a couple of tasks here. So one of them, I think, is a sentiment analysis. Yeah, I guess, yes, exactly. So and the data set is IMDb. So this is the litmus paper of any NLP. So if you do a classifier, you need to train. Well, you should train it on the IMDb data set. Maybe not today because the IMDb is so much everywhere that it's even leaked in the training data for GPT and things like that. So maybe not today. And like nowadays, it's not relevant anymore, or it doesn't tell you really about the performance. But it used to be like, well, you should train on IMDb, which is a binary classification. So there's like positive and negative classes. And 50,000 documents. Okay, so 2 classes, 50,000 documents, and it's a movie review. Okay, so the movie was great, positive, the movie was bad, negative. with more nuances in the text. So we took IMDb, then we took Stanford Natural Language Inference, which some of you might remember from the previous lecture, is the natural inference task saying, if I have a piece of sentence, if I have a hypothesis and a piece of text, does this hypothesis entails the text? So I don't know, like for example, what is the example? 10 men are playing football would be one piece of text, and the other would be there are persons playing football. Then if this is true, then it entails the other is true, but because it's like a generalization. If 10 men are playing football, there are people playing football, so it would be true if this is positive. The negative would be 10 men are playing football and the sun is shining today. So it's like it's a neutral, and there's contradictory as well. So this is Stanford Natural Language Inference data set. So, and it's quite huge. So it's like 500,000 pairs of these sentences and 3 classes: entails, contradicts, and neutral. Then we have NER. So any ideas what NER is? NER? It's named entity recognition. Exactly, saying like, oh, in this piece of text, each word is either no entity or it's a person, city, date, company name, and usually we use BIO tagging. So it's like beginning of the entity and inside of the entity. So there is multiple classes here, and there are 2 data sets which are somehow standard ones. So we look into this, like not only text classification, but also like token classification. And a similar is POS. So anyone guessing what POS could be? It's part of speech tagging. So part of speech tagging means, well, this word is an adjective, this word is a noun, this word is a verb, and stuff like that. So it's very kind of linguistic task or typical NLP task. And we took these 2 data sets. And the last one, which is different from the above, is question answering. So the SQUAT 2.0. And if I remember correctly, the details is that you should basically answer a question by selecting where in the paragraph the answer is present to your question. So you have a paragraph, let's say from Wikipedia, a long paragraph, and then a question, something about the paragraph, and you should locate the actual position of the answer in there. As far as I understand it, but you have to fact check me on that one. But basically, it's answering questions on some Wikipedia pages. So these are typical NLP tasks, and we took them like we were interested in. Okay. So first assumption: let's pretend these data sets are private. Obviously, they are not. These are just public, and everybody knows them. But these are prototypical tasks that are used, across all research in NLP, and we pretended like, well, this is private, so let's train DPSGD on top of that and see, is there any pattern? I mean, are some tasks more difficult than the others for the privacy setup, or how does it work? Because nobody knew back then. And as you might see, okay, so we do different models. One was a BERT. What was it? BERT performance? Is it BERT? Oh yeah, this is BERT. And you can fine tune. So okay, fine tuning of BERT. So who knows what fine tuning of BERT is? Or let me put it like that. Who doesn't know what is fine tuning of BERT? Okay, BERT. BERT. Everybody's on board? BERT? Good. Fine tuning of BERT? Not really. Okay. Pre-training of BERT? Not really. Okay. So BERT is this transformer model, and it has so many parameters, but the trick why it really works is that you initialize this model randomly, so random weights, and then you do the self-supervised pre-training, so to say. So you take a sequence of words, remove one word from the sequence, and try to predict the missing word from the remaining words around it. So you take maybe like a chunk of text, lots of chunk of text from the internet, always like mask few words, and then try to predict back the word. So, and by using that, you're learning all the weights of the model, and you learn something about the language. It's similar to GPT, but in GPT you take a chunk of text and try to predict the next word. And through that, you're learning also the weight. So you're predicting the future. In BERT, you're predicting something somewhere in the middle. While doing this, you pre-train the model, and so it kind of learns something about the language, like GPT, and then you do the second step. For your data set, you fine-tune it. So it means you take your, I don't know, sentiment analysis, and then let the model to learn. So you put something which is called the classification head on top of it. So there's one single layer on top of the BERT model and saying, okay, now learn for this particular task, learn in the standard supervised learning and update your weights. And then the question is, okay, so now clear a little bit? Okay, cool. And by doing this, so-called fine-tuning, well, you can do many things. You can say, well, okay, let me learn the full BERT, like all the parameters of the BERT, which could be like millions of parameters. Or you can say, well, I just want to learn the last layer of BERT, or I just want to update a few layers of BERT, because BERT has some layers as well. It's a deep neural network. And the question is like, well, some of them works better than the others, because now we have to know like what does it mean for privacy. Well, in privacy, the more parameters you're updating, the more noise you have to add, because the more dimensions you're trying to protect in a way. So the gradient is kind of, it's a bigger vector. Okay, so this is an unknown thing. So anyway, as you might guess from the title of this paper, one size does not fit all. There's actually no clear strategy how to do it across tasks and across different training strategies. So we try to use, for example, BERT with fine-tuning the full BERT. Yeah, this is awesome. So for example, here I'll take one example here, just to highlight one of these examples. So I guess this weird symbol, this kind of butterfly or what it is, for this privacy, so this is basically no privacy. This should be infinity, right? So, and if you fine-tune the full BERT for this particular task, you get the best performance. Okay, so this is the best model performing non-privately. Oh, this is great. And if you just take, let's say, last two layers of BERT, which is this circle, and fine-tune it non-privately, you get very few performance, because you just, I don't know, like the model learns less from this task. But surprisingly, with privacy, so this is epsilon here, right? And the more to the left you go, the stronger the privacy is. And now everything basically flips. So the model which was the best performing, so fine-tuning the full BERT with no privacy, once you add privacy, the performance drops to something almost random. While if you train just the two last layers, the performance goes up. Why is that so? So this is a big question, like about interpretability of BERT, but as you might see, this is one example, but you don't observe it in the other data sets, for example. So what we would be expecting is that the more privacy, everything goes down, but that's not the case, because it also depends on the training regime. So what can we learn from this? Well, in general, yes. If you add privacy, so more privacy, more to the left, the accuracy goes down. In most of the cases, like here, this is clear. Here, this is clear. This is mostly random answers. It's very bad. This is also like very nice trend. So this is kind of corresponds to our, what we kind of expect. Yeah, if you add noise, something will be worse. Like the accuracy will be worse. But in some cases, it's not the case. And, we kind of had a couple of hypotheses. Why is this so? I don't have answers, because, why some model performs as it performs, it's a research question. So you have to do maybe some probing of these tasks. So we had a couple of hypotheses in this paper, but the message taken here is that if you have a hammer and you have a big model, and the model, the more data and the bigger the model is in the non-private setup, it doesn't guarantee you it will behave in the same way in the privacy setup. So if you add privacy, things will change, and you have to just basically try it out on your data, on your task, with your privacy guarantees that you want to achieve. So this is the message kind of taken from that, okay? Non-conclusive. So I don't know. I mean, if you have a task at hand and you have a model, you have to try out what works best with privacy you want to achieve. So there's no best solution ever. Okay, any questions? Good. So now let's move to something less obvious. So now, for now, we have this training data set, and we kind of assume like each example in this training data set is one person, and we apply the standard argument of fine tuning with DPSGD. Okay, let's move to language models now, and some early language models with differential privacy. So this is a paper by Brandon McMahon and others from Google from 2018. And here the language model is basically something like GPT. So having a few, they use much simpler model, not GPT. But having a few words, you want to predict the next word. And they were back then in 2018, they were using like for a mobile keyboard, something like, how's it called? Like Gboard is the application on Android. You have the Gboard or Google keyboard, which kind of suggests you the next word. I mean, if you're typing on mobile, it gets you the next word. How that works is this is it. I think this is actually it. Like they're actually using this technique now in Google, keyboard, even with privacy, I would assume. So how that works is that given the previous couple of tokens or the whole sentence, you get your suggestion for the for the next token, and you just select it, and it makes it easier to type. And of course, your data is sensitive, right? You don't want to give your whatever you type in your message, you don't want to give it just to, you don't want to give it to Google to train their language model, because someone else can just share it. I mean, if you type, okay, well, my name is John Doe and my social security, my PIN is 12345, and you share it with Google. Google trains a language model which is shared and for all people, and someone else just writes, oh, my name is John Doe and my PIN is, and the model would suggest 12345, then that's not what you want. So there needs to be some privacy protection. So what these guys try is actually to combine two techniques, and I'll be talking about them in a detail in a minute, to protect the privacy of the users' tokens or what they write, and to do it in a way that it can't be shared with the data don't have to leave the phone. But here is that what they propose was kind of different, or what is a new proposal of this of the neighboring data set. So most prior works on differential private machine learning have these kind of example level privacy. So we have two data sets, D and D prime, and they're using the word adjacent, but neighboring is the same, so this is the same word. If D prime can be formed by adding or removing a single training example from D. Okay, so this is the standard like table, remove LEs and call it a day. Awesome. The thing is, here, that a sensitive word or phrase may be typed several times by an individual user, but it should be still protected. So we're moving now from a table of people to a table of sentences or messages, and they are not independent anymore. So there is information which is present in two of them maybe. So what can we do about it? Well, we can ignore it, but that's maybe that's not a good solution. The better solution is that what they propose here is so-called user adjacent data set or user neighboring data set. So, and it's a very easy trick. So we have, again, D and D prime, two data sets of training examples where each example is associated with the user. Okay, so we have an example. I have the example, so I'll show the example later. D and D prime are adjacent if D prime can be formed by adding or removing all of these examples associated with a single user. Oh, okay. So here how it is. So we have data set of some four examples. So training examples. This could be a sentence, for example. A1, A2, B1, B2, and A and B are the users. So which means A1 and A2 belongs to user A. So Ellie's messages, and B1, B2 are Bob's messages. Okay, makes sense? Good. So we have, this is the data set, and we know which one belongs to which person. So then D prime can be formed by adding or removing all examples from one user. For example, we could remove Bob from here to get A1, A2, okay? Or we can add one person like Charlie. So this is another neighboring data set. And obviously we cannot do something in between. So like just removing one example doesn't give us this neighboring, user level neighboring data sets. Okay, so this looks kind of obvious and it looks correct. But as we will see later, maybe this is not like maybe this is not a definite answer how to protect privacy. But for now, let's pretend this is okay. Let's pretend this is really okay, and then train the, we have neighboring data sets, so we can use the typical tricks we have in DPSGD. So their kind of their language model relies on two prior works, and one is the federated averaging. So I'll talk about it on the next slide, which trains deep networks on user partition data. Okay, so whatever it means, like federated learning is a thing. And of course, it depends on the DPSGD. So DPSGD is this moments echoten by Martina Badi and Gaussian mechanism combined with amplification via subsampling. So this is what we know. The second part, this is what we talked about last time. And this is somehow new, and they combine these two techniques. Why they combine these two techniques is that this federated, sorry for this, it's a lot of text here. I wish they had the graphics in the paper, but they didn't. So I took the text. But this federated averaging is a federated learning. Okay, so where the goal is to train a shared model. So we want to have a model, for example, what is the next token given the previous tokens? But the training data will never leave. Well, the training data will reside or leave on the mobile device. So you have people, they have mobiles, but you never give your data away. How you do that is that instead, each mobile downloads the model from the server. So if we have that will be a server, there's a model, and we have a couple of mobiles, then in each step, you download the full model on each device. Then you perform here the gradient updates on your training data here and send it back. And there is some averaging of this thing, and you need to protect these gradients as well. So you made an update and repeat in the next step. This is basically how federated learning is working in a nutshell. So you don't share your training data, you keep it on device, but somehow share the model and then do these sort of client-server exchange. Okay, so, and what is important here, that their algorithm naturally performs per user updates. Oh yeah, okay. Based on single user's data. That's true, because each user has only their own data, their own messages, but not others' messages. So this is like private, one person, one person, one person. And these are then averaged to compute a final update. So once they send together, you make an average, and this gets you the gradient. So it's basically the same as if you have a batch of batch in stochastic gradient descent, you also do the averaging for each instance. But here the instances are kind of distributed. Each of them computes a gradient and send it back to the server, and the server makes the average. Okay, so this makes it actually possible to extend the algorithm to provide user-level differential privacy guarantees. Okay, cool. So this is nicely works together. I won't go into the actual details of that, what they used, because there are a couple of extra steps, and we're not going to talk about federated learning in this lecture. But what they use is that they select the users independently. So in each step, they say like, oh, I'm gonna take this one, yes, and this one maybe not, and this one maybe not. This is basically the very same thing as this subsampling, where we said in the last lecture, each of the examples in your training data will be taken with some probability, yes or no. So you randomly take a subsample. And this randomly taking of subsample gives you this amplification of privacy, as we saw. So you get much better privacy kind of guarantees for this one iteration. So that's what I did. I'm sorry. I need to turn this down. So they're also performed some clipping per user updates. So, okay, we need to again make sure that these gradients are kind of bounded, so we can apply the DP noise. I don't think we need to spend some time on that, because this is off the differential privacy perspective. And then finally, they added the Gaussian noise to the update. So this is basically the DPSGD. Okay, so they combined two things. One is this federated learning with differential privacy to achieve kind of differential private language model, which is distributed across mobiles. And here's some little bit of details on the data and evaluation. So they use a large public data set of Reddit posts. I think this is something we should remember for the later discussion. So Reddit posts, Reddit. So everybody knows Reddit. What is Reddit? How does it look like? What is in there? Like what's the structure of Reddit? Yeah.
It's divided into multiple different subreddits.
Okay.
They all like have a certain topic. For example, there's a subreddit about politics, subreddit about whatever.
And then
you can make posts in those subreddits.
And then
text, and then there are comments on the.
Okay, so there are comments. So this is like a thread. So typically a tree-ish structure. Okay, this is interesting. Keep that in mind. So Reddit, you have posts in Reddit, and these are it's a discussion. So people are reacting to each other. Okay, so this is not like I write something about myself and that's it. But if I have a comment, it mostly relates to some, if I'm not the OP, the original poster, I'm maybe related to something which is above. Remember this. But for now, let's ignore it and basically say, well, each post in the database is associated with an author. So they group the data by these keys in order to provide us a level of privacy. So what they do is saying, like, if you have this is a discussion, and if this is no, not like that, doesn't make any sense. But if this is written by A, and this is also written by A, and this is also written by A, they basically couple all these A's and say, well, this is one user's data, and this is, how we group them together, and maybe these will be the other user data, B's. Okay, so they just kind of make them associated with each user, and then they apply this user level privacy as we discussed. Okay, is it clear? Awesome. So they ended up with I don't know, like this number of users, and each of them roughly some 1,600 tokens, whatever. Okay, so this is the preparation of the data set. So this is an interesting assumption, and the actual model that we're using is not GPT. It's something I would call old school nowadays. This is LSTM, long short-term memory language model. So if you don't know LSTM, that's okay, because it's it's old technique for old problems. It's like recurrent neural networks. A recurrent neural network, which has been very popular before GPT. So it's like a small-ish, 1 million parameters. It's big for LSTM, but if you compare it to, I don't know, 7 billion parameters of Llama 2 or things like that, then it's a small model. And what they were evaluating a language model. So if you do language modeling, there is a metric called perplexity, and it's something, it has to do something with cross entropy and things like that. So it's like there is a standard things to evaluate language models. What they were using were basically simplifying this, just if the first word that I'm going to predict matches the missing word, then it's a hit. And if it's a mismatch, it's a 0. So it's basically accuracy of the first word. So for example, if I say a sentence, I want to go home. Oh, I don't want to go home. I don't want to finish the lecture. I want to finish the, and then the model will predict the next word. And the first word would be, the true would be lecture. And the model predicts lecture. It's like hit, it's accuracy. Sorry, it's 1. And if this predicts, I want to finish the breakfast, so it's wrong. Okay, so this is accuracy top 1. It's not really standard techniques for, it's not a cross entropy, but whatever, they use that. Okay. And here is the interesting thing. So we're gonna ignore this C parameter because the evaluation is much more complicated, and you can have a look at the paper. But what's interesting here is that if you have no privacy in this setup on this Reddit data set, there is some accuracy of 17%. And once you start plugging in privacy with epsilon 4 to even like epsilon of 2, the drop in accuracy is actually not that huge. It's worse, but not that worse. So this is interesting, and I actually, I don't know why. I mean, they don't say why is that. They just claiming, well, these algorithms work so well that objectively measuring, there is a drop, and it's not huge. So epsilon of 2 Is it good or not? Well, I don't know. But if you recall randomized response, so randomized response at epsilon of logarithm, what was that? 3, which is something like 1.1 something, I guess. And randomized response is considered kind of safe, or like if I ask you, do you take drugs? With randomized response, you will give me the answer. So epsilon of 2 is actually pretty good for language models. Epsilon of 4, who knows? But maybe it's still considered good by some people. So the drop is actually very minor. So this is interesting, and it's actually good. I mean, this is like one of the examples. If we can trust these results, I think you can reproduce these results and just play around with these models. This is an achievement. So you have a differential private language model which protects the users. This is awesome. This is what we want. But it comes with a couple of assumptions as we talk. For example, this assumption of the data set. Maybe there is something fishy about it. But let's consider it as a solid work. It's on archive since a couple of years. I don't think it was actually, yeah, it's ICLR. So it's one of the very cool ICLR, very cool conferences. So seems legit to me. So just a side note, all research is considered wrong. I mean, most of the research is, so I'm not talking about this particular paper. So, but in general, research, if you see results, take it with a grain of salt, always. The more you're in research, the more kind of the pessimistic you're getting about everything you see, because some things are basically, if you try to reproduce them, you will find something else. And not only in computer science, like in all areas, there's a reproducibility crisis in psychology, for example. It's an issue. So if something is published somewhere and it's peer reviewed, might be okay. And most likely, like top journals or top conferences, the ratio of papers which are good or correct is higher, but not 100%. So there are things that are just kind of wrong because nobody paid attention, or just, well, things can be buggy or whatever. So, but I'm not talking about this particular paper. I don't know. So I think like you can just download the data, the code, and try to run by yourself and kind of, can you reproduce the results? Can you really kind of reproduce the claims they're making? Can you do another data set and stuff like that? But in general, transparency and reproducibility is important, so then you can verify these results. And if you talk about privacy and security, this is even more important, to be able to check whether whatever you have and claim it's secure is really secure. So you have to be able to double check that. Anyway, so this was, I would say, like, well, less obvious application for DPHGD, but still good. Now, well, what happened? When things go tricky. So what does it mean? Yeah, okay. Okay, so we have this, again, the subsampling amplification, or Poisson subsampling, which amplifies privacy. So just to reiterate again, what was that? We have a data set of A, B, C, D, and E, which is in our kind of training data. And the Poisson sampling is saying, well, for each of them with some probability P, I'm gonna say, well, is this going to be now subsampled in the data or not? So maybe this one is subsampled, maybe this one not, this one not, this one yes, and this one not. So I will end up with something smaller, which will just contain A and D in this example. And if I run a DP algorithm on this smaller data set, then I get much better privacy guarantees, like much smaller epsilon and much smaller delta. Because there was some randomness that, well, if I were this person, I will not end up in this data set, in this analysis. So this is how the Poisson subsampling is working, and we talked about it in the last lecture. The thing is, if you do machine learning or supervised, machine learning, sorry, if you do supervised training, and typically in neural networks nowadays, you have your training data set, which is A, B, C, D, E. So this is Oriole examples. And what you do, how do you treat the training data? So typically what people do is random shuffle. So we would get something like, I don't know, B, C, A, ED. And then how do you split your training data typically? What do we use? We use some subset of the training data. How do we call them? Remember that? Yes? Training test and validation is different. Oops. Training test and validation. After you do your training test and validation, so consider this as just a training data. So what do you do with your training data? So for example, you have 50,000 of these things, like A, B, C, D, and so on, 50,000, and you wanna do stochastic gradient descent. So what do you need to do? Because you won't fit in the memory of your thing. So what is it? Batches, exactly, batches. So we have these micro batches, and if we had, for example, here, so batches or micro batches. Also micro batches. So for example, for micro batch size 2, we take then this one will be batch number 1, this one will be batch number 2, and maybe if I had 6 of them, it would be like the last batch, something like that. So then we have these micro batches, and we do the stochastic gradient descent, the update of the parameters over one batch. So the data is pre-shuffled, then you cut them in the batches, and then you do for first batch, do the gradient step, the next batch gradient step update, the next batch gradient step update. Then you repeat, oh, let's start from the first batch again, gradient step update, the next batch, and so on. So basically you iterate over these batches. This is like 99% how like typical frameworks, PyTorch, TensorFlow are working. So you shuffle the data because you don't, you want to have it shuffled. You want some randomness. You shuffle the training data, then cut it into batches, and then just go batch after batch after batch, next epoch, batch after batch, and so on. Okay, so there is some randomness, but this is not the randomness as we need for the formal proof of this Poisson sampling. The Poisson sampling is saying for any update, if you want to do subsample, you have to randomly say for each of them whether you're going to sample it, and then, sometimes it will be size 2, sometimes size 3, sometimes the size will vary. There is no single batch, but you have to do this step to be really differential private. So the good news is this is correct. This is like formally, there's a proof that it actually does what it does. The bad news is everybody's using this. Everybody's just using this with differential privacy on top of that and saying like, oh, yeah, this is a tiny little detail and we just can ignore it. So Timur with Doan and Felix, Jo, Yannick, and myself, we are actually looking into how much this is important or not. So is there a difference if you do this Poisson sampling, which is really, really, really correct, versus if you do this kind of, what everybody's doing, just batches and call it a day? Is there any difference? And we took neural machine, machine translation. I think I have an example on the next slide. Yeah, neural machine translation. So we're interested, like, okay, well, this is correct, but it comes with a cost that, again, there's extra cost for that, because you need to change the batch the batch size for each iteration. You need to do the sampling, so everything will be kind of slower as compared to this. So there is some complexity with the Poisson subsampling, which if something is slower in training, then the difference is if you can train for a week versus a month will make a huge difference. Yes?
One question about the subsampling.
Yeah.
The subsampling once before you start training, or would you do it?
No, you have to, yeah, the subsampling. So this is a good question. I mean, whether you have to do it like just once and then you have this. No, you have to do it in every step, before every update of your gradient, you have to do the subsample. I don't have the algorithm here on the slides, but basically you say so you have epochs in the differential privacy. So excuse me, in SGD. So you say, okay, for epoch number 1, there's a training data set. Now give me a subsample by this Poisson sampling. You get a subsample, and then on the subsample you run the gradient the loss computation, the gradient, the updates. Next epoch means, oh, give me again a subsample. So this subsampling has to be done for every iteration. Basically, before any kind of gradient computation or loss and gradient computation, you need to subsample, because this will guarantee you this privacy amplification. Anything else you do, there is no guarantee whatsoever. It will work, but you're losing this kind of things formally. And nobody actually cares about it, more or less. So we look into like, well, is there a difference? So we took for neural machine translation, if you've never done neural machine translation, basically we have data sets which are kind of standard. So for example, WMT16, if you never heard of that, that's okay. If you do anything with machine translation, this is the first data set you're gonna see. So this is a standard data set for, I think it's a workshop on machine translation, 2016. And there are German English language pairs. I think we had this homework on that, like taking WMT16 and do something, try something, hands-on with that. Okay, so this is standard data set, and then the sentences are mostly very boring, some politics and some newspaper and things like that. So, but you always have a sentence in one language and the same translation in the other, or several translations in the other language. So this is standard, and we took it, okay, as a reference, sure. But then, there's nothing private in it. But we are interested in like, oh, maybe there's something more like private data or private-ish data. And there's one, actually, there's two we took, which are interesting. This is business scene dialogue corpus, which is like fictional business conversation in various scenarios, such as like face-to-face business dialogue, phone call, or meetings. So this is kind of fake data. Obviously, if these were real data, you have no chance to get them. But these are, mimicking like how you negotiate about contracts in company. And why is this important? Well, this is a dialogue. So there are some, this is a dialogue. So this is an important feature. And there are some, customer names, how much money you're going to pay them for the contract and things like that. And these are considered to be private. If you want to train your machine translation model on your private company data sets and provide this model to someone else, you better train it with something like differential privacy. Otherwise, someone can steal your internal things from the trained model. You can do that, as we know already. So this is one data set we took. And the other is actually also interesting, is clinical cases for COVID. So I think there are some personal data in this. I don't remember exactly the details of this corpus, but it's considered to be somehow sensitive because there are some clinical notes of people in there. So we took those, and as you see, like they vary in size. So we have over 4 million training points for this WMT because it's big, and the smaller one are just much smaller. The other one are just much smaller. Excuse me. And here's the thing. So of course, if we take, and this is a good and bad news. Good news is we try different epsilon privacy budget. Again, the more to the right we go, the less private it is. And epsilon of 0 means like basically no privacy, and epsilon of 1 means something like a strong privacy. So the blue score, the higher the better. If you've never done anything with blue score, does it ring a bell? Everybody knows blue score? Okay, awesome. So it's a metric for some sort of lexical overlap of the reference translations. Excuse me. So the higher the better, but it shouldn't be like very, very high, because then you're not generalizing well. So there is a rule of thumb, like around 40 blue score is awesome, and below 20 it's kind of bad, or 30 is kind of bad translation. So if we train, so this is like non-private models. So we have a reference, how well can we perform these tasks. So as we see, for this large data set, of course, we can get blue scores over 30. So this is good. And for smaller data sets, we are just much worse, because these data sets are, first of all, the languages are, so the Japanese, for example, is kind of tricky language to learn for parallel translation. So it's much harder, even with like full data set and no privacy. And the clinical one is also tricky because there's like medical jargon in it. So the medical domain makes it hard to do machine translation in general. And now now if we take the privacy into account, if we go to the left, there's this drop, and this is so brutal, then maybe it's completely non-usable. You see here epsilon of 1000. Now, who believes here that epsilon of 1000 is private? I don't. I'm not at all, because e to 1000 over, I just do the math, and the chance it will be revealing the true data is so high that basically it's like almost 100%. So epsilon of 1000 is just for the reference to see like where we go. And we see some drop here, and some methods actually can only start with no, excuse me, no, this is just of course for a comparison. So when we start from epsilon 1000, go to 5 and 1, we see here, I mean, on these examples, everything is bad. So maybe we should forget this, because this is like completely bad. Like the results are just rubbish. The translation is, the noise is so bad that it just breaks anything that the model can learn, because these domains are already hard for the non-private stuff. So I mean, these are already bad enough. And if you add noise, this is just completely useless. So let's forget these. But now let's have a look on these on the WMT, where we have a lot of training data. And this is good news or bad news. So basically, if you do it correctly with the Poisson sampling, then it's much harder. Like the performance is just much worse than if you do the standard random shuffling thing. So what does it say? Well, it says that if you ignore privacy, like if you ignore the formal requirements for privacy. So for example, if you say, well, I'm going to do DPSGD, but I don't do the Poisson sampling, I just do the random sampling. So you get better results, of course. Yeah, but you're basically breaking, the formal privacy guarantees. If you do it correctly, your results will go down. This is a bad news, basically. So doing privacy for real is tricky, and you cannot ignore just one part of it and saying like, well, I consider this is okay, because this is not, because the difference is then there is a difference in performance. Okay. So if you do everything correctly, I mean, if you do it incorrectly, you get better results. But there's nothing like to be incorrect. I mean, either it satisfies differential privacy or not. And this one breaks differential privacy as we want. I mean, this breaks the sampling amplification. So this is wrong. So this is why it's tricky. When things go tricky, they go tricky. Anyway, so any questions to that? I mean, it was like just a showcase, like that if you want to do it for real, it's getting harder. But now let's move to things which go very tricky, and we will have some thoughts for some what do you call it, like something for the brain to think about. So what is the again? We're coming back. I mean, we started with this private information text. We started a couple of weeks ago. We started with entities and all these things, and anonymization, and everything was kind of okay unless it was bad. So we said, okay, let's forget it. Let's use differential privacy, which is super formal and super nice. Now we're getting back to the text and seeing like, oh, maybe this is actually still hard or impossible, as we will see. So what is private information text? So the thing is that it's not really clear, because the application of differential privacy, that we guarantee that each individual data point is protected. As we saw today, for textual data, a single data point will often be a sentence or document, right? So we have I don't know, one sentence in the machine translation, or one post in this Reddit forum, or one document in sentiment analysis. This is sentence. But this doesn't mean that there is one-to-one mapping from individuals to sentences or documents. Remember, what we can do with differential privacy is the database, Alice, Bob, Charlie, Dave, and so on. We have the database. But if we have texts, we cannot be really sure that this is true. Maybe sometimes it is, maybe sometimes it's not. But we have to be very careful about it. So the first example of training, fine-tuning a bunch of examples like the sentiment analysis, this is fine. So we may actually treat one review belongs to one person, and this one person is revealing just the information about itself in this one single text. Okay, this is maybe fine. But sometimes maybe not. So for example, multiple documents could potentially refer to the same individual, because maybe this is talking about D somewhere, and this is also talking about D. And now we're breaking the main assumption we had in the very beginning, that each row has to have information about only itself, because where it comes from, this database, is just secrets of, bit secrets. Okay, taking drugs, diseases or no, and nobody else knows anything about this person or the secret bits. But if we have documents and text can tell something about other people. This is where it's getting very tricky, like this kind of the very assumption of this independence. And I think I'll have an example in the next slide, just to highlight that. So there is a very, actually, I would like you to read this paper. So if there is something you can do, is to read this paper. Because this is like really eye-opening. Because you know differential privacy, you know anonymization already. And this is very accessible paper, open access paper as well. Accessible in terms of like no heavy mathematics. It's just basically you read a paper and you understand every single point. So read this paper. This is very important. So in this paper, they discuss the mismatch between the narrow assumption made by popular data protection techniques. Okay, narrow assumption, like, oh, we have database in differential privacy, or we have data sanitization, which is anonymization like entities, and the broadness of natural language and of privacy as a social norm. Okay, this is interesting. So they're basically putting this into perspective of what people who understand as privacy again in text. And they argue that existing protection methods cannot guarantee generic and meaningful notion of privacy for language models. Okay, this is a strong claim, because as we saw like this federated differential privacy language models is saying like we have privacy with differential privacy for language model with a tiny little drop of accuracy, and this is awesome. And what they're claiming is like it's impossible to achieve. So who is right, who is wrong? Well, I don't know. This is research, so the one who has stronger arguments on or empirical evidence is correct. But let me show a couple of examples to kind of highlight this. So, okay, just to let me see what's here. The approach preserving privacy in the language model has been to attempt complete removal of private information. So, okay, again, data semanticization or algorithms that do not memorize private data, such as differential privacy. Both methods make explicit and implicit assumptions about the structure of data to be protected, the nature of private information, and requirements for privacy that do not hold for the majority of natural language data. Okay, this is interesting. So again, basically saying the same information that was previously on the slide. But I think like one picture is better than 1,000 sentences. So here we have a conversation of Alice and Bob. And it goes like that. So, hi Alice, how are things going? Oh, not great. Did I already tell you I'm getting a divorce? Oh no, I'm sorry to hear that. What are you doing to do about custody of the kids? And here so this is a made up example, I guess, in this paper. And they indicated this is a private information. So did I already tell you I'm getting a divorce? So this is something Elise is telling to Bob. And this is, by the authors now, in this social context, is considered as private. Why? I don't know. Why this is exactly private and not, why this is considered private and not other things are considered private? It has something to do with as we as humans consider as privacy in social norms. And this is what the paper is about. So that's why I want you to read it in detail, because it gives you this perspective of, beyond just plain computer science, theoretical differential privacy stuff, but more about like what humans understand as privacy, which is getting, again, very nasty and arbitrary. Anyway, so they say, well, this is the original conversation. Okay, so what can we do now to protect Elise? What can we do to protect this information of Elise? So if you want to train a language model, so what can you do for protecting Elise? What would you do? The first thing, what would you do? You want to protect Elise information. You want to train a language model. So what are you going to do with this thing? What comes to you? The first thing that comes to your mind. What can you do to protect Elise information? You can anonymize something, so you can, but there's no entities in here. So what? Even like the more simple thing, what can you do? Like the simplest thing you can do to protect Elise. Yeah, sure. Done. Just delete Elise completely, right? I mean, you're protecting Elise by deleting all her messages. Awesome. Will it work? Where's the catch?
problem is that we can also get this information messages from
For example?
custody.
Oh, yeah. Okay. So Bob is saying custody of the kids. And if you're smart enough or ask GPT, you will know that custody of the kids has something to do with somebody getting divorced. So yeah, I'm sorry. This is exactly, yeah, I mean, sure. I mean, you know, there's no silver bullet here. So we're influenced as messages, but Bob's last message still includes her private information. Now, remember this Reddit language model where we grouped messages like that and that, and we called them independent. But they were not, because nobody has checked it. They just say like, yeah, if this belongs to one user, this is independent of the other. Who knows? Because this is what most likely, I mean, this is what most likely will happen. If people talk to each other, they kind of refer to what has been said before. Otherwise, it wouldn't be a conversation in the first place. So this is, and like, that's what I said. I mean, I don't think like the paper from Brendan McMahon is bad, like technically or in other things, but maybe the assumptions in there are just wrong because they don't protect what they think they protect because of the trickiness. What we consider, again, I mean, technically it's super bulletproof, I guess so. I guess they're doing like the best job technically, but the data set actually is not meant to be, you know, worked with like that because of these trickiness. So okay, this is tricky. So what can we do next? So let's okay, no, I'll come to that later. So what can you do? Like, I mean, if you want to protect Elise completely. So now we know that now we know if we delete Elise, we know that we know this about Bob. So what can we do more to protect Elise? The next step would be, can you continue your argument? Can you continue your argument? Good, I agree. Okay, so let's delete it from the training data, okay? Now we're protecting Elise. Okay, cool. So what can go wrong? Many things. You're losing data and whatever. Wait a second. I mean, this is what we did. And here there's another conversation, and there's Charlie and Bob, and Charlie's saying, "Hey Bob, how you been? Well, pretty good. I think WBU is like hub. What about you? Right? Okay. WBU. Oh, did you hear Alice is getting divorced? Okay. And this is it. I mean, we have another documents, another people. Alice is not even involved directly. Even if he said, "Oh, did you hear my best friend is getting divorced?" Even if there's no entity. So I mean, if there's Elise, you could do some, you know, entity checking and whatever. But maybe, oh, did you hear my best friend is getting divorced? And then, you know, Elise information is leaked through somebody else. Again. So what can we do about it? So I don't know. And I don't think anybody knows. And I think this is very, very, very tricky. It goes to the heart of what again is privacy? Is it the same as security? What if you tell somebody about something which you consider private? So, okay, I think we should stop recording and we can talk, because this is something like, I want to know your opinion as well. So for everybody's watching on YouTube, thank you for watching on YouTube. Next time, just, you know, maybe come here and we can have a discussion. And let me just stop recording.